All right, so we're on chapter 7 in the Red Stewart Calculus text, the Calculus of First Course. And on page 298 is where you find some of this material. So this is just review and preview, as we do most chapters. I like how this textbook is set up. They give you a little bit of a review and preview to the chapter for the necessary sort of pre-calculus information that you need. So that's what this is. We're just going to go over a few things to make sure that we're all on the same page with some things that you already have learned. You did this in Pre-Cal 30, area of a sector. So if you have a circle, a sector is a portion of the circle where it's kind of like a triangle, right, with a curved bottom, which is the part of the arc of the circle. And involved in this is a central angle, okay? So a sector has to have its vertex really here at the center. So we have an angle theta, and we have a radius, and we have arc length. And so these are related. Those three units are related. So let's just take a look here. So the region of circle cut off by two radii, so this is a radius emanating from the center, as I mentioned, is called a sector. The sector angle is the central angle there. And if we're trying to find the area of a sector, okay, we whittle this down, and the sector area turns out to be 1/2 r squared times theta. 1/2 r squared times theta. Okay. And so if the r theta as actually A, so A equals r theta, that's the one that we worked with a lot last year. A equals r theta. So if we take an r out of here and a theta out of here, we have 1/2 AR. So the area there. Okay, so arc length is radius times the central angle. That's what we learned in Pre-Cal 30. The sector area then will be similar to a triangle area, except because you have this curved bottom, it has to be adjusted a little bit. So it's 1/2, and then the base and height are actually the arc length and the radius. So 1/2 AR is where that comes from. So calculate the area of a sector with an angle 2. Okay, so that would be radians, and our theta does have to be in radians if the arc length is 3.5 centimeters. So let's see. So the sector area is 1/2 AR. And A equals r theta. We're going to have to find out A because the arc length is 3.5. So this is A. A is 3.5. Okay, but we aren't given the radius. So I guess we have to find the right to calculate the area. Arc length is given. So the radius is going to be A divided by theta, A over theta. So 3.5 divided by 2 radians. Sometimes your angle will be in terms of pi. Sometimes it'll just be a numerical radian measure. So R is, was that 1.75 for a radius. So you go back here and you fill in all the values. 1/2, 3.5. times 1.75. And that turns out to be 1.75 squared, I guess, which is about 3.0625. And centimeters, and its area, so it's centimeters squared. Okay. So you're going to want to remember probably well, both of these are good to remember, I guess. Sector area is 1/2 r squared theta. Also, if you're given the arc length, then you might want to remember this other formula for sector area. So let me just zoom in on those formulas. Make sure you have those down. So next is inverse of a function. So you recall in Pre-Cal 30, inverse, you want to think reverse. So inverse means reverse. And what are we reversing? We're reversing the coordinates of each point on the original function. And so the inverse is going to have points y comma x. So 0, 0 is going to be the same, obviously. And anything that's on the y equals x line. So let's say this is the y equals x line. So if I have, let's say this is approximately -3, -3, let's say, then that point is going to be an invariant point, right? It doesn't change. It's going to be on the inverse as well as this one. That point is going to be on the inverse as well. So every other point, again, if we had coordinates, you just reverse the y and the x and you plot a new point. So this one is x, y. So now we want to go y, x, right? So that is up here somewhere. And the other thing that you remember too is that each point is the same distance away from the y equals x line formed at a perpendicular to that line. So if you take the distance from any point and you just send it across that line, you're going to have sort of your new point. Okay? So this is going to come something like this, right? It's going to be a mirror image of this sort of part right here. So this part right here is going to make a little bit of a heart shape, I guess. All those points are going to be a mirror to the y equals x line. Okay. So something like that. So the blue graph would be a graph of the inverse. Okay, does everyone see that? So if you draw that y equals x line and you were just basically to kind of like rotate the graph around that y equals x line, that's what your inverse looks like. And if we checked a couple points, like this point, let's say I'm guessing this is maybe, let's just say this is like a 7, 3, right? Well, then this point right here should be 3, 7, right? On the blue graph there. And so on. 0, 0 stays 0, 0, right? Yeah, so 3, 1, let's say, becomes 1, 3 up here, and so on. So it's a reflection about the y equals x line. Excuse me. Now, the other thing we need to talk about too is, functions, right? So, do we have a function? Is the inverse a function? That's going to be something that's going to be asked of you. And so, if we do a vertical line test on this blue graph and we draw a vertical line anywhere, if it passes more than one time through the graph, then it's not a function, right? So the inverse is not a function. Here, not function. Okay, the original graph is a function though. The red graph is a function because any vertical line on the red graph would only pass through once. Okay, so let's talk, well, actually, let me just skip ahead here. Yeah, so if we're talking about functions here, remember that a vertical line test would pass through the graph only once. And what that means is a function, for every x, there's only one y value associated with it. If there was more than one y value associated with an x value, it's not a function. Function notation, if you remember this, the function or the y value is a function of x. So each y is associated with one x, that kind of thing. Or I should say each x, when you input it into the function, it spits out only one y. Okay. These are all functions, the first three. Passes through just once, anywhere you draw the line. This one, not a function, right? Passes through 3 times in some places. So that's not a function. Now, when we take a look at the inverse, okay, how do we know that the inverse is a function? That's going to come in, well, let's do that right now. So the horizontal line test is the test for the functionality of an inverse. So horizontal line test, and we have talked about this, but it might be distant from your memory here. So if you draw a horizontal line through a function, that's how you tell if the inverse is going to be a function or not. So if a horizontal line passes through the graph more than once, then the inverse is not a function. That's what the horizontal line test tells you. Because if you think about it, okay, a horizontal line such as this one right here, this horizontal line, if you were to take the inverse of this line, becomes a vertical line, right? The inverse of this line, so if this is the y equals x right here, okay, the inverse of this yellow line becomes this vertical line. And so if you're testing the functionality of the inverse, you draw a horizontal line on the original graph. So let's just see here. So for this parabola, I'm going to draw an inverse. So that's going to come sort of like this, right? It's going to come down like this. Okay. So that's going to be kind of like that. It's a bad drawing, but kind of like that, right? So if the red graph is a parabola, opens up, then you flip it around the y equals x line. So you can see that this yellow line that I had there before, let's see, that cuts the graph more than once. So the inverse is not a function. Okay. And if it passes the horizontal line test, like over here, this graph right here, if this is our original graph, it passes the horizontal line test. The inverse could look just like this line. That's the inverse of it, right? If it parallels the y equals x line, then this is the inverse, and of course, it passes the vertical line test too. So if it passes the horizontal line test, the inverse is a function, and that's quite possible as well. If you think about, for example, this one right here passes the horizontal line test, therefore the inverse will be a function. Yeah.
So is this a normal function that you do the horizontal line test on?
Yeah. You test the original function for the horizontal. Excuse me. So if the horizontal line passes through the graph, this would be the original graph right here. Yeah. The graph of f of x. The inverse notation, I don't know if we talked about that. You guys remember what the inverse notation is? I believe it's f to the negative 1, right? So the inverse would be f to the negative 1 of x. Yeah, that's the inverse notation. So I would like to talk about the inverse of trig functions because this chapter is about trig functions. So let me just see here. Yeah, I think this would be we'll wrap up our preview here. We will talk about inverse of trig functions because we're going to be talking about limits of trig functions in 7.1. So the black graph, okay, so the black graph here is y equals sine x. Now I've exaggerated this so that it's easier to draw the inverse. So it doesn't look like semicircles, right? I've exaggerated this just a bit. It's easier to draw this way. But let's say that this black graph is the sine of x graph, okay? The inverse, if you were to carefully draw the inverse, and I will try my best to carefully draw the inverse here, okay? And I'll just draw it for a section, okay, just for a part of a section there. So, oh wow, I hit the erase button there. Okay, so if the black graph is the original sine graph, if I just sketch the inverse for a section, okay, obviously this would keep going, wouldn't it? Like this, and like this. But you can tell that a horizontal line going through sine, the sine graph, would intercept the graph many, many times. And so the inverse of sine is not a function. Okay, sine is a function, the inverse is not a function. And yeah, the graph is flipped from a wavy graph going horizontally to a wavy graph going vertically. And this is what the inverse sine function. Now, I don't think you guys have seen this before, but sine to the negative 1 of x would be a way to notate the inverse sine. The only problem with this is this function on your calculator. You see, there's a function like this on your calculator, and we usually use this function to isolate for an angle, right, given a sine ratio. So in calculus, you'll find that this is not used as much as something like this. And maybe you've seen this before on a calculator in a textbook, arcsine. So arcsine, arccos, arctan, that is inverse. That's how you denote inverse for a trig function. So I'll use this one most of the time, arcsine or arccos. So again, this is the inverse of y equals sine x, arcsine. And yes, we're going to be doing derivatives of arcsine, and we'll be doing integrals of arcsine as well. So we'll be dealing a little bit more with the inverse function. Okay. Now, one more thing I'll just mention: the usefulness of the arcsine is really only it's mostly useful as a function. So we restrict the range of the arcsine. So usually it's just where it is a function. So if you look carefully, I'm highlighting the section, okay, one section of arcsine that is a function. So that is a function. So a lot of times when we deal with arcsine, it's restricted in its range so that it's actually a function. But that'll come later. I'll talk a lot more about arcsine later, but just so you have an idea of what the inverse of sine looks like and what it's called. Okay? You good with that so far? Okay. Arcsine. Okay. Talked about this already. Skipped ahead to this. Okay. Yeah. This many-to-one function, I'll just mention this. We did talk briefly about this in pre-cal. Many-to-one is opposite of like one-to-one function. So a one-to-one function are functions like this, where there's only each y value has only one x value. And you're like, I thought that was what a function was. No, a function is every x value has only one y value. But in a one-to-one function, each y value also only has one x value. And these would be examples of one-to-one. Many-to-one functions would be like this. So check this out. I have a y value, y1, that is the same y value for many x's, yet this is still a function. Okay, so this is an example of a many-to-one function. This x has y1 as a partner. This separate x has y1 as a partner, and this third x here has y1 as a partner. That's called a many-to-one function. And many-to-one functions are the ones that do not pass the horizontal line test, right? Because if you draw a horizontal line, that means that it trips through more than one point. And so a many-to-one function has an inverse that is not a function. So a many-to-one function has an inverse that is not a function. And I'll maybe write that down right here. Has an inverse that is not a function. And again, this just coincides with the horizontal line test. Okay, so it's another way to think of it. Horizontal line test is really like a graphical drawing, right? If you have a list of points and you see that there's the same y value in more than one point, you know it's a many-to-one function. You know the inverse is not a function. So the horizontal line test is graphically the understanding what a many-to-one function is. If you just consider the points, that's a way you can determine whether the inverse of the list of points there is a function. But I'm going to take a look at properties of limits here as well before we launch into chapter 7, because we're going to be using these quite heavily. So again, you can refer back to this. I believe this is on page 13 in your text if you want to look back. Properties of limits, pretty straightforward. If you have, if you're taking the limit of a polynomial or a group, an addition or subtraction, right, of different terms or functions, let's say, then you can take the limit of each function separately and either add or subtract. So that the first two are pretty basic. This one is interesting, right? If you have a constant multiplied by a function, you can pull the constant out in front of the limit. Like it's as x changes, the constant doesn't change, so it can be pulled out. That's your constant term sort of limit property. Multiplication, okay? So it's not like the product rule if you're taking derivative. Limits, if you have a product, you can just take the product of each individual limit. Same with division. Okay? If you're dividing, you can separate the limits. That's what we did in chapter 5, finding horizontal asymptotes, let's say. The last two listed here, if you have an exponent on a function, you can actually find the limit of just the function only and then take that limit to the value of n, okay? If n is a positive integer, that is. And similarly, if you have an index here of a root, then you can take the limit separately and then take that root of the whole limit value. So these are virtually the same because the index of a radical is a fractional exponent, right? So it's really just both exponent laws. I don't think. Trying to think of all the questions we're gonna have here. I don't think we'll run into 6 and 7 all that much at all. But anyways, okay. So that's the properties of limits, and that's your little review and preview to chapter 7.